this is a continuation of the homework 7. So this is problems 10 through 16. Although I'm skipping 14 because number 10 and number 14 are pretty similar. So anyway, this is number 10. So this says you have measured concentrations in a constant volume batch reactor, and you need to determine the order of the reaction and the rate constants. So you have T and Ca, and then you have data, and it says find order of reaction and rate constants. So the way you go through these problems is, first of all, you postulate a rate law, and so this would be minus Ra is equal to K Ca alpha. And then if your reactor type is a batch, which it says it is in this case, then you know that the mole balance for a batch reactor is minus Ra equals minus dCA dt. So you haven't talked about a differential reactor yet. I don't know if he's going to, but that's the other type of reactor you could have that you would look at, that you would run experiments and tabulate data and then calculate K and alpha. So anyway, then you can combine these. So 3. And so you have minus, actually, so you have minus dCA dt is equal to K Ca alpha. And then from here you can go a couple different ways. You can either go so if you take the natural log of this, you get the natural log minus dCA dt is equal to ln of K plus alpha ln of Ca. So then by now you should recognize that this is actually a straight line, or the equation for a line. So then alpha would be m, and the natural log of, or b is the natural log of K. So then if you get your equation in this form, then you calculate dCA dt, and then you plot the natural log of dCA dt versus the natural log of Ca, and then you do a linear regression to get this line, and then you should be able to calculate K and alpha. And so really, if you go this route, the big part of this problem is calculating the dCA dt. And you can do that with a few different methods. First, there was the graphical method. And so for number 14 on this assignment, this is basically the same type of problem, and in the solution he used the graphical method to calculate dCA dt. But you can also use the finite difference equations, and those are in your book, so if you look those up, that's just plug and chug if you use those. And then for number 3, which I think that's going off the screen, so I'll write it really small up here, polynomial. So you can calculate your polynomial, and then basically the way you do the polynomial is you plot this data, CAT, and then you fit it, and then you'll get some polynomial, and then you can take the derivative of the polynomial with respect to t, and so then you can get dca dt. So anyway, no matter what method you use, you get dca dt, and then once you have that, the problem is the same. You just take the natural log of it, take the natural log of ca, plot the natural log of dca dt versus the natural log of ca, do a linear regression, and then you'll get an equation like this, mx plus b, and then you can calculate k and alpha. So the other route you can take when you solve these is the integral method. And that's actually the route that he took for solving this problem in the solutions. And so for the integral method, you guess alpha. And so you say, okay, alpha is 0, or alpha is 1, or alpha is 2. And then you solve this equation. So you basically integrate it. And so for instance, if you guess 0 order, you would end up with an equation that looks like Ca is equal to Ca naught minus Kt. If you chose, say, I'm going to erase that because it's kind of getting in the way. So if you chose, say, first order, you would get an equation that looks like the natural log Ca naught over Ca is equal to Kt. And then there's also one for second order. So then what you do is you plot this. So for instance, for 0 order, you would plot Ca and T, and you should get a line. So just coming up here, if you plot Ca versus T, and your equation is Ca is equal to Ca naught minus Kt, then you should just get a straight line. And so, and the same thing for this. So for this one, you would plot the natural log of Ca naught over Ca versus T. And if you do that, you should also get a straight line with that one, because you have natural log Ca naught over Ca is equal to Kt. And then I'll just write down the second order. So that was, I'll just write it up here. So the second order was 1 over Ca is equal to 1 over Ca naught plus Kt. And so then for this one, you would plot 1 over Ca versus T. And with that, you should also end up with a straight line. Basically, the point is, if you don't end up with a straight line, then you know that you guessed alpha wrong. So then you would have to go back and try another one. And and then once you have this plot, then you can calculate what k is from. So you can do a linear regression, and then you can calculate k. So where this gets complicated is, for the integral method, is if the order isn't 0, 1, or 2, then you can still use this method, but you have to use nonlinear regression to calculate your alpha and k. So I guess it's hard to say if he puts a problem like this on the exam, it's hard to say, for me to recommend a method, because it's, honestly, if a problem like this showed up on the exam and I didn't know what the order was, I would probably go with this route and probably do the graphical method. Or the other thing I've done is if you can calculate the polynomial on your calculator and then go from there. And I've done both of those, and you should be able to do either of those on the exam without too much trouble. If you go this route, the reason why I would be leery of going this route is because I don't know how to do nonlinear regression on my calculator. If you have a way that you know how to go about that on your calculator, then this method's probably fine, but I would be worried about just getting stuck, like going through these and not finding the order quickly, because usually on an exam you're trying to get through the problems quickly. So like with this method, especially if you went with graphical, it's pretty straightforward, like do this, then do this, then do this, and there's not a lot of guessing, it's just stepping through the steps. So that's why it's kind of hard to recommend a specific method for this. And so and I'm not going to go through the exact solution for this because it's on the solution he gave you, but so for problem number 10, he used the integral method, and so he guessed, well, maybe I'll just write it down. So he used the integral method and he guessed second order, which it turns out it actually is second order. So like if this was on an exam and you said, okay, second order, and solved it, then and then you would find out that it actually was second order, then this would be pretty fast. But if you didn't know it was second order, and say you guessed zero order and then first order and then second order, that's going to take some time to go through those. And so that's why I was like, okay, well with this method, it takes some time to get DCADT, but once you have that, it's pretty fast to step through things. But so I'm going to go through the solution he had for number 10 real quick, I guess, and then just for number 14, he used the graphical method to get DCADT. And so I'm going to show you how to do a linear regression on your calculator. I hope you already know how to do that, but just in case, if you don't, if a problem like this shows up on the exam, that's probably something that you're going to want to know how to do. So, okay, so for number 10, so he had the following data, so T, CA, and then he guessed that it was second order, and I'm not going to go through the calculation of that, but it's basically a second order batch, and so I already know that the equation for that is 1 over CA minus 1 over CA naught is equal to KT. So this is the integrated equation that you get. And you should know how you get this by now. So you go through the mole balance, the rate law, and that's why with this one you're guessing what alpha is, or you're guessing what this is. And so in this case, he guessed that it was second order, and so when he integrated this, he came up with this equation. So then we can plot, like if I rewrite this as 1 over CA is equal to 1 over CA naught plus KT, then what you want to do is plot 1 over CA versus T. So then you can see so you plot, so I would have another column here. So I have the data for T, CA, and then I'd probably want to do another column and just calculate 1 over CA. And then you can plot the 1 over CA versus T on your calculator, and you'll get some line, and so we'll probably end up looking something like this. It's not very straight. Sorry, I almost drew it through 0, but it's not 0 because there's some intercept. So anyway, you get this line, and then you do a linear regression, so you'll get a y equals mx plus b, and then you know that, so the b should be 1 over CA naught, and then m is k. So that's how you do the integral method. And so what he came up with for this problem was y is equal to 0.178 x plus 0.171. So then k is equal to 0.178. and then alpha is 2 because it's second order. So on this problem, you would know if you guessed wrong because you wouldn't end up with a straight line. So anyway, now I want to pull out my calculator. And I'm just going to write down this data real quick that I'm going to put in here. So I'm plotting 1 over CA versus T. So 1 over CA, this was 0.2, 1.075, 2.44, 3.7, 5.56. And then T was 0, 5, 13, 20, and 30. So I have a TI-89, and if you don't, I mean, I'm assuming you probably already know how to do this on your calculator, but if you don't, definitely review it, because if he has a problem like this, there's a pretty good chance you're going to have to do a linear regression. And I mean, you could do it by hand too, I guess, but I just think it's, I don't know, I like to do it on here. So anyway, on the TI-89, first you would go to apps, and then there's an app called Data Matrix. So you go to that, and then I'm just going to hit, so then it says current, open, or new, and I'm just going to go to current because I already had this open. And then it has, so type, and so for type you want to choose data, and folder doesn't matter, and just put something in for variable. I'm just going to put in so the variable is kind of like your file name, so just put something in for that. So then I'm putting 1 over CA on the first row, so that's going to be, actually no, I'm going to put T on the first row, because that's, so you have C1, C2, and C3, so I'm just going to put in T, so 0, 5, 13, whoops, 20, and 30. And then for the second one, 0.2, 1.075, 2.44, 3.7, 5.56. So I don't know how well you'll be able to see that on here, but I have like C1 and C2, and I've put in the data. So then you can go to calculations, and so then on calculation type it says 2 variable, and so you have 1 variable, 2 variable, cubic regression, exponential regression, linear regression. And so for this, what you want to pick is the linear regression, and then you want to select your variables for x and y. So for x, so the first, I put the data that you have in whichever row corresponds to whichever. So like you had C1 and C2, and I put T in C1 and 1 over CA in C2, and this corresponds to x and this corresponds to y. So the first one would be C1, and the second one would be C2. And then you can say store regression to, and you can, like I'm going to store it to y1x, and if I do that, then I can plot it. And so I usually when I do these, I plot the data and the regression so I can see if they look right. And so for linear regression, I mean, I've never had it not work out, but like if you're, say, doing a cubic regression or trying to get a polynomial or something like that, then it would be more important to make sure it looks right. Okay, so y1, so then I press enter, and it gives me so then it gives you this screen that says stat variables. And so it just says y is equal to a x plus b, and then it says a is equal to 0.178 and b is equal to 0.171. So that's what he had gotten. So anyway, that's how you do that. And if you don't want to do this on your calculator, you could plot this and figure out where the y-intercept is, which should just be 1 over CA naught. So let's go back here real quick. What was CA at 0? Well, yeah, so, I mean, according to this, it seems like it should be 0.2. It's coming up with 0.171, which I guess rounds. But anyway, so, I mean, you could, I don't think that you're required to do this on your calculator for the exam. So you could carefully plot this by hand and then calculate the slope. So that, I mean, that's another way to do it. So then if you want to plot this stuff, go back into apps and then data matrix and then go to current. It should come back up. It should bring up what you had already. And so then you can go to plot setup, which is F2. If you hit F1, so I've already defined mine. So what you're doing is you're defining what you're plotting. I don't know if you can see that very well, but so it comes up with this thing and it has plot 1, plot 2, plot 3, etc. And then says F1 define, F2 copy, F3 clear. So what this is doing is this is plotting this data. And so if you hit F1 to define that, then first of all you want to choose a scatter plot because you're plotting data, so it's not technically a line. And then you can choose what mark you want. So I'm going to choose a box. And then you can tell it what x is and what y is. So I put in x is C1 and y is C2. And then you just hit enter to save. And it should tell you that it should show that there's something there on the plot 1. And then you can toggle this on and off by pressing F4. And so if there's a check beside the plot, then when you go to graph, it'll plot it. If you undo the check, then it won't plot it. So I'm turning the check on to plot it. So then I can get out of there. So then you can just press the green button with the diamond and then graph. And then it should plot your data. So the boxes on here are the data, and the line is the linear regression I did. So then you can kind of check your stuff. So for number 11, this says, the following first order reaction is taking place in a PBR, so this is 11. And it says, okay, so first order, whoops. And it's a PBR, and this is your reaction A to B, and it gives you the reaction rate and constants. So the rate is equal to K PA, and K is equal to 0.75. And then it says A is fed to the reactor with 50% inerts, so 50% inert, and T is 327 degrees C, and P is 1 atmosphere. And it says the feed rate of A is 37.5 moles per hour, so FA naught is 37.5 moles per hour. The pressure drop parameter alpha is 0.0045 kilogram minus 1. And it says, obtain an expression that relates the conversion in the reactor to the weight of the catalyst. State your assumptions. And it says, what conversion can you obtain with 100 kilograms of catalyst? So W is 100 kilograms, and it's asking for X. So the first thing you want to do with this problem is a mole balance. And so the mole balance for a PBR is, and also this is asking for a conversion, so you want to write your mole balance in terms of conversion. So dx dw is equal to minus Ra prime over Fa naught. The rate law was given as minus Ra equals K PA. Next is stoichiometry, and you have Ca is equal to Ca naught 1 minus x over 1 plus epsilon x y. And remember, y is because you have the pressure drop. And oh, and then well, I'll get to that in a minute. Okay, so pressure drop. So this is dy dw is equal to minus alpha over 2y 1 plus epsilon x. So if you remember with the pressure drop, okay, so he's asking for you to come up with an analytical solution for this, and you know that because he's asking you what conversion you can get when the weight of your catalyst is 100 grams. And so the way that you come up with the analytical solution for this is you need to figure out a way to solve this so you have an algebraic expression that you can plug back into here. Because right now you have two coupled ODEs, and maybe there's a way to get an analytical solution for that, but I wouldn't want to do it, especially on an exam. So the way you can do that, the assumption you need to make is you need to say that epsilon x is approximately 0. And if you do that, then you can integrate this and solve for y. And so when he's saying state your assumptions, make sure that you specify that you're assuming that epsilon x is approximately 0, because if you just write, because what you end up getting once you say that's 0 and solve this is you get y is equal to 1 minus alpha w to the 1/2. And so this is correct, but the problem is if you don't specify that how you got that you assumed this, then technically this is wrong, because you have to state your assumptions when you do things. So you can't just pick off this equation and use it without, like, you have to justify why you're using that. So anyway, if you do that, then you can plug this into here. And then this equation, so our rate is in terms of partial pressure, but this is in terms of Ca naught. So what we can do is just say Ca is equal to Pa over RT. And so then we know that Pa is equal to Ca RT. So then when I plug this into here, I'm going to actually use this for Pa. So combining all that, I get dx dw is equal to K RT, so Ca naught. So here's where I basically just put this into here and this into here. So 1 minus x, 1 minus alpha w to the 1/2, and this is all over FA naught. And so I also said this was 0 when I assumed that epsilon x was equal to 0. So then the CA just became CA naught 1 minus x y. So then I can combine these. I know that this is P A naught. And so, and I'm just doing that to kind of simplify this. So I can, and then I want to separate and integrate. So 0 to x dx over 1 minus x is equal to k PA naught over FA naught 0 to w 1 minus alpha w to the 1/2 dw. So then if I integrate this, I get minus natural log 1 minus x is equal to k PA naught over FA naught 2 over 3 alpha 1 minus alpha w to the 3/2. So then I know what FA naught is because it was given. I know k because it was also given. I know w and I know alpha, and I'm solving for x. So the only thing I need to solve this is PA naught, and I know that PA naught is equal to YA naught, so it's the mole fraction of A, P naught. And I can get the mole fraction from the problem statement. It says that it's 50% inert, and so I had A to B coming in. So I know if it's 50% inert, then it has to be 50% A. So this YA naught is 0.5. So then the PA naught is just 0.5 multiplied by P naught, which was 1 atmosphere. So that's just 0.5 atmosphere. And so then I should have everything I need to plug in and solve for x. And if I do that, I get that x is equal to 0.58. So number 12. Says you have a first order reaction with no volume change. So first order, V is equal to V naught. It's a PFR. And you have 20% conversion, so X is equal to 0.2. And then it says the engineer realizes that he has 4 times the size of reactor available. So he has another reactor that's V is 4 times the volume of the PFR. So I'm just going to say volume PFR, and so 4 times the size of the reactor available, but some mixing is essential. So it says he engineers a recycle reactor to get 50% conversion. What recycle ratio is necessary to achieve the design conversion? So this is the first reactor. And then the second one, you have a recycle reactor. So this is the second one. And for this one, X is equal to 0.5. And then he wants to know what R is. So just as a quick review for R, so I'm going to draw a recycle reactor here. So you have some stream coming in, some stream coming out, and then you have a stream that comes off and feeds back in. So if you start naming your streams, so this one is usually FA naught, and so Fogler uses a few different terms for some of these things than what you've been seeing in class. So I'm going to try and point those things out, but just when you're dealing with these recycle reactors, just make sure you're really clear about what the different streams are. So FA naught is usually what's flowing in from out here. And then you have a stream here that's usually called FA1, and FA1 is a combination of FA naught and this recycle stream, which is usually called FAR. And then coming out, you usually have FA2 immediately, and then FA2 is, well, so FA2 splits in FAR, and then this final stream, which can either be called FA3 or it could be FA final. So just make sure you're clear about what stream you're talking about when you name these, or when you're looking at equations, just make sure you're aware of what terminology they're using. And then this applies to all of the species, so this would be like FB naught, FB1, FBR, FB3, etc. And so R is the ratio of this stream, the recycle stream, and the stream going out, like after FA2 splits. It's the ratio of FAR over FA3. And this R is the same for every species. So this, you could say that this is R is FIR over FI3. Basically the problem is asking for R. And so what you can do is this, and I already talked about this a lot at the review session, and I think on another video, is if you get a recycle reactor problem on the exam, you probably want to jump straight to the integrated equation. But I highly recommend knowing how that equation was derived, because I can't guarantee that he won't ask you to derive it or to give you some data for a reactor and ask you to derive that equation. So definitely be familiar with how to derive it, but in this case you can just jump straight to the integrated equation. And so you know it's first order, so the recycle reactor first order equation is K tau R plus 1 is equal to the natural log Ca naught plus R CAF over R plus 1 CAF. And so it gives us it gives us X, and X isn't in this equation, so we need to figure out some way to relate. Well, basically, so we know what Ca naught is, I think. Okay, so in this case, we actually don't know what Ca naught is, so you need to, so looking at the conversions, so this conversion that's giving us this X equals 0.5, in the recycle reactor, that's actually X naught. And X naught is the conversion out here, like the conversion of everything. I think it's also called XF. And there's also a conversion here, which is XS. So just be clear on, also if you're playing with conversions and recycle reactors, just be really clear about what conversion you're talking about, because you can also have a conversion here, and this would be XA1, because when your feed stream comes back and combines with this, there's going to be some A and B or whatever's in there that's been converted. So you just need to be clear about what you're talking about. But when it's giving you this X equals 0.5, that is, it just says the recycle reactor gets 50% conversion. So I guess I'm making an assumption that he's referring to the final conversion for everything. So anyway, we need, so X naught is equal to Ca naught minus CAF over Ca naught. And so then if you solve this for CAF, CAF is equal to CA naught 1 minus X naught. So then you can plug this into here and get this equation in terms of CA naught and X naught, and CA naught should cancel out. I'm going to erase this real quick. So if you plug CAF into here and into here and do some math, you end up with an equation that looks like K tau over R plus 1 is equal to the natural log 1 plus R 1 minus X naught over R plus 1 1 minus X naught. So then you don't need CA naught because it cancels out. And I just got confused for a minute because there was another recycle reactor problem that he gave you that you were still working in terms of X naught, but you didn't need to actually convert the equation over because you could calculate what CAF was from this equation because he gave you CA naught. And so then you could just calculate CAF using X naught, plug it in, and then solve for whatever it was you were solving for. But in this case, since you don't know what CA naught is, you need to put the equation in this form. Because you can't calculate what CAF is since you don't know CA naught. So anyway, so looking at this, we want R. We know what X naught is. The thing that we're missing is K tau. And so we can get that from this PFR because the K, so K should be the same, and the volumetric, well, okay, so K should be the same, and tau, so tau is equal to V, V over B naught, and then it told us that the recycle reactor was 4 times the size of the PFR, so then this should just be multiplied by 4. So you can get tau K and just multiply it by 4. So I'm not going to go through the math in detail for the PFR, but if you go through a mole balance, the rate law, stoichiometry, and you know that it's first order, no volume change, you end up with an equation that looks like this. So K tau is equal to the natural log 1 over 1 minus X. And so then, and you know that X is 0.2, so then you can solve for K tau, and you get that K tau is equal to 0.2231. So then you take this and multiply it by 4, like I just talked about. Plug that in for that and solve for R. And if you do that, you get that R actually, I didn't write down the answer for R, but he gets that R is equal to 3. So anyway, that's how you do that one. So with these recycle reactor problems, if I got one of these on the exam and it didn't tell me to derive, like if he doesn't say to derive the first or second order or whatever, like if he says, like if you're not having to derive this integrated mole balance equation, then I would first write down the equation that so for instance, this one he said it was a first order recycle reactor. So then I would write down this equation. And then it said, and then you know you're looking for R. So then you can just look at this equation and be like, okay, well, I want R, so I need to figure out what CAF is, CA naught, K tau. But then it's like, oh, I don't actually have CA naught, so but I need the equation in terms of x naught anyway, so then I can just solve this equation for x naught for CAF, plug that in, and then you get the equation in this form. And then looking at this, it's like, okay, I still need k tau, and then you know that you have data from the PFR, so you can calculate that. And so that's how I would approach these problems, because I think if you just start writing things down like this, like this integrated equation, and then it's just going to start coming what you need, like, because you're just going to look at it and be like, okay, I need this and this and this, instead of trying to think about it before, and just getting freaked out. So then, like with this equation, if you were given this in like this other problem I was thinking of, where you didn't actually have to plug in the CAF and solve for x naught, you were given x naught in this other problem, and I think you were also asked to calculate r in that, but you were given x naught and you were given CA naught, and so then you didn't have to go through plugging this in and doing that math, because you could just calculate CAF since you knew CA naught and x naught, plug that in for CAF, and then you can just solve this for r. I mean, you would still do the same thing to get k tau, but so that's all I'm going to say about that. But just make sure that you're pretty familiar with the equations for recycle reactors. Like I would be definitely familiar with this, and then the one for the second order. I would know how to calculate x naught. I would know how to calculate xs. I would probably want to know the relationship between xs and x naught. And yeah, just review those, basically what was on the homework, and you should, if you do get a recycle reactor problem, you should be able to figure it out. Number 13. And I went over this problem in the review today, and I kind of butchered the end of it, so I'm going to go through that again in better detail. And this is the good thing about videos. If I screw something up, I can just kind of erase it and redo it. But anyway, so this says that you have a second order elementary reaction. So this is second order elementary, and you have A plus B to C plus D. It says you have a semi-batch, and it's at 25 degrees C. So I'm just going to write the rate constant is 0.5 at 25 degrees C. 200 moles of A are loaded into the reactor, so Na naught is equal to 200 moles. And the initial volume of the reactor is 990 liters, because if you remember with a semi-batch, you're adding to it, so the volume is changing. And says B is flowed into the reactor at a rate of 15 moles per minute. So FB naught is equal to 15 moles per minute. The volumetric flow rate is 1 liter per minute, so V naught is 1 liter per minute. And then it says derive and write down the ordinary differential equations for the conversion A. So the conversion, so XA, conversion of A so it wants you to find XA in terms of all known parameters and the initial condition that you would use to solve this ODE. You do not have to solve the ODE. So I'm going to start with that, and then I'll do the second part. So if he asks you to write down equations, like if he asks you to write down equations and not solve it, just make sure that you're really clear about what, like with problems like this, at least when I had the class, they were usually looking for the exact equations you would put into a numerical solver, so like Polymath or MATLAB or whatever. So I would be pretty clear about, okay, these are the equations I'm putting in, these are all my constants, just so there's no room for question like, oh, did they actually know, like even though you have Na naught in your equation, just write down that you're putting in 200 moles for Na naught, because otherwise he might mark you down and say, oh, well, he has that in the equation, but did he actually know what that he was going to put in 200? So just make sure you're really clear about what you're putting in. So anyway, for this problem, first you would do a mole balance. And so you use the mole balance for a batch reactor. For a semi-batch, you use the mole balance for a batch reactor, and then the difference is your stoichiometry is different because whatever you're adding is so yeah, I mean, I'll get to that in a minute. So you have minus Na naught dx dt is equal to RAV, and then you have the rate law, and it tells you it's second order and elementary, so you know that this is minus RA equals K CACB. And then for the stoichiometry, you have, for A, you have that CA is equal to CA naught, sorry, so CA is equal to NA over V. After a while with these equations, sometimes I just start writing in autopilot. So anyway, so it's important I think that for a semi-batch, it's important to write your equation starting out in this form, because what I was just writing, so if I had have written CA is equal to CA naught 1 minus X, that would be correct if my volume wasn't changing. So like if I just had a pure batch reactor and the volume wasn't changing, then this, or like a flow reactor that the volume isn't changing, then this is correct because you can just divide V through. But in this case, the volume is changing because we're adding fluid to the reactor. So if I had have written that first one, it would have been wrong. So anyway, so I know that Na is equal to Na naught 1 minus X, and then V is the initial volume plus whatever is added. And so you can calculate what's added with just this volumetric flow rate multiplied by time. And then CB is NB over V. And so this, in this case, we're adding B. If you were adding A, then you would write A like this and vice versa, but we're adding B. So just be careful with that on the exam, because he might try and trick you by saying, oh, we're adding A, when every single equation or problem you've solved, it's been B that's been added. So just make sure you are clear about which one's being added, which one's already in there. And then also, if you, like, I would write the equation, so NB is equal to NBI, so whatever's in there initially, like in this case, we know initially this is 0, but I would write it down anyway, because what if there was some in there initially, and then you just like didn't write that down, because say you're used to just writing, like what this usually comes out as is NB is equal to FB naught T minus NA naught X. So let's say you're just used to writing this down and you forget the NB initial, then this would be wrong. So I always start out by writing the NB initial plus, and then you have what you're adding, so that would be FB naught T, so the flow rate times time, and so then the time cancels out and you just end up with moles. minus Na naught x over V naught plus V naught t. And also be careful with this last part because this is based on the stoichiometry. Like if so, we know that the same amount of B as, so whatever A reacts, the same amount of B reacts, but like if this was A plus 2B, then this would be minus 2 Na naught x, because for every A that reacts, you're reacting 2B. So just be careful about that too. So then this is 0. And then you can just combine all of this. And so what I'm going to do is put that in there, that in there, that in there. So I'm going to erase some stuff real quick. I end up with Na naught dx dt is equal to k Na naught 1 minus x over V naught plus V naught t multiplied by F B naught t minus Na naught x over V naught plus V naught t. And then this is all, so this is also multiplied by volume, and just be really careful to make sure you, so I mean the volume is this V naught plus V naught t. So you can't just write in V because this is changing. So anyway, then you can cancel this, this, and you end up with dx dt is equal to k 1 minus x multiplied by F B naught t minus Na naught x over V naught plus V naught t. And also when you're writing this volume and the volumetric flow rate, just be really careful to write them so you can distinguish them. So this is really what he's asking for, because he said don't solve it. So yeah, yeah, he says you do not have to solve the ODE, but you do have to write down the initial condition that you would use to solve it. So the initial condition is, you know that when t is equal to 0, x is equal to 0. Erase some stuff and then do the second part of this problem. For the second part, it says the reaction is operated in the semi-batch mode for 10 minutes, at which point it stopped. So it's operated in semi-batch for 10 minutes, and then it stopped. And after that, the conversion was x equals 0.25. And then it's continued in batch mode, so we stop at adding B. So just batch for another 10 minutes, and then it wants to know what is the overall conversion of A, so x A, and what is the overall conversion of B. So the way you do this is, I'm going to erase this over here too. What you need to do is figure out what the conversion is in the second part in the batch reactor. You already know what it is in this. And then you can, once you know the conversion in the batch reactor, then you can calculate what you have for Na and B, and you know what it is from here. So you know what you started with, and you can calculate what you end with, and then you should be able to calculate these overall conversions, because the conversion that you have in here in the batch reactor is not this overall conversion, because you already had some conversion before that started. So for the batch reactor, it says you have a second order batch. So then you can do a mole balance. So you have Na naught dx dt is equal to minus RAV. And you know that the rate is equal to minus RA is equal to K CA CB in the stoichiometry. So CA is equal to CA naught 1 minus X. Now I'm going to take a step back real quick. So CA is equal to NA over V. If you remember, that's what we had for the semi-batch. And I mean, this is what it is for this too, but the difference is, so we know that Na naught is equal to, well, Na is equal to Na naught 1 minus X. And then in this case, V is equal to V naught because there's no volume change, so this is just V naught. So then you get Ca naught 1 minus X. So just be clear when, like, if you're dividing your volume through, just make sure that you can. If your volume's changing, like in the case of the semi-batch, you can't just do this. So then CB is equal to Ca naught theta B minus B over A X. So then we can combine everything, and so if you do that, you get that, let's go up here, dx dt, so this is combined, is equal to K Ca naught, because I'm just plugging these in, squared. I'm going to take a step back. I was kind of skipping some steps, but I'm just going to write the whole thing down. So Na naught dx dt is equal to K, and then I have Ca naught multiplied by Ca naught, so Ca naught squared 1 minus X multiplied by theta B minus X multiplied by V. And then this is the same thing I was just talking about. So in this case, V is equal to V naught, so I can divide the V over, and so then I have Na naught over V, and that's equal to Ca naught. So then I can cancel, like if that's there, then I can cancel that and that. So then I get dx dt is equal to K Ca naught 1 minus X theta B minus X. I'm going to erase some stuff because this is getting kind of messy. So if I integrate that equation, I get K Ca naught T is equal to 1 over theta B minus 1 multiplied by the natural log of theta B minus X over theta B 1 minus X. So then in order to solve this, I want to solve this equation for X. And so I need Ca naught, I need the volume, and I need theta B. So we already know what Ca naught was, and I'm going to actually write this down because this is where I got kind of confused before. So for the first reaction, this was the semi-batch. We know that Ca naught was well, Na naught, so Na naught was 200 moles. We know that X after 10 minutes, so T was 10 minutes. We know that X was 0.25. So then we know that, oh, and then volume V naught was 990 liters. And V naught was 10, I think. So this was 1. So 1 liter per minute. Okay, so for this we need Ca naught, and so the Ca naught we're looking for is what we're starting with in the second reaction. So second reaction, which was the batch. And so we started out with Na naught was 200 moles, and then there was some conversion. And so the conversion that we had in this reactor is what we start with, or the Na that we have after 10 minutes in this reactor is what we start with in this one. So we know that Ca naught is equal to Na over V. And we know that Na naught, so we know, so this is equal to Na naught 1 minus X. This is what you have after this conversion. And then V is this V naught, the initial volume, plus V naught T. So then this is 200 multiplied by 1 minus 0.25, and you get 150 over, and then this is 990 plus 1 times 10, so this is 1,000. So then Ca naught is equal to 0.15. So I'm going to write that over here, so we know that Na naught in this reactor is 150, and Ca naught is 0.15. And then we need to calculate theta B. We know what the volume is because I just calculated it, it's 1,000. So theta B is equal to N B naught over Na naught. And the mistake I made in the review session is I used the Na naught and NB naught from this reactor, and they should have been from this reactor. So we already know that Na naught is 150, and so we need to calculate NB naught. And so we can do that. We know that NB, so this NB naught is the NB naught we have in here is, so you started out with a certain amount of B. You actually start out with 0, but you added some. So you know you can calculate how much you added, and then you can calculate how much was reacted because you know what the conversion is. And so then you can figure out what amount of B you start with in the second reaction, and that will be NB naught. So NB is equal, and we calculated this. This was this equation where you had the NB initial plus FB naught T minus Na naught X. And we already knew that this was 0. So NB is just equal to this. So this is, so it gave us FB naught as 15 moles per minute. So FB naught was 15 moles per minute. So this is 15 multiplied by 10 minutes minus Na naught was 200 multiplied by 0.25, and that was equal to 100. So then this is 100, and so you end up getting 0.667 for theta b. So then you can plug theta b, Ca naught, K, and T into this equation and solve for x. And if you do that, you get that x is equal to 0.3. So then in the second reactor, you know that x was 30%. But that's not what it's asking for the problem. It's asking you what was the overall conversion of A and the overall conversion of B. So I'm going to erase this. But the overall, so the equation for x is equal to Ca naught minus Ca, like whatever your final is. This is, in this case, this is actually moles. So this would be Na naught minus Na over Na naught. And then for B, so this is Xa, and Xb is equal to Nb naught minus Nb over Nb naught. So we know what Na naught is because it's given. So this is 200. And then we can calculate what, so we know the conversion in this reactor, and we know that let's write this down here. We know that Na is equal to Na naught 1 minus x. So if we put in, that's not right. So Na naught starting in this reactor was 150 multiplied by 1 minus 0.3. And so then you get 105. So this is 200 minus 105 because it's what you started with and then what we ended with in the second reactor. This is over 200, and then you end up with 0.475. And then for the second one, we can calculate exactly how much Nb we started with in the first reactor before any conversion happened, because we know, and that would be Nb naught. Nb naught is what you start with. So we know that the amount of B added to the reactor, so I'm just going to call this Nb naught, is equal to Fb naught T. So this would be the rate that it was added, so 15 multiplied by the time that it was being added, so that's 10. So this is equal to 150. So then we have that we started with 150, and then we want to calculate how much B we had left at the end of the second reaction. To get Nb, we can use this equation. We know that Nb is equal to Na naught, and this is B in the second reactor, so Mb is equal to Na naught multiplied by theta b minus x. And we already calculated theta b, and we know what Na naught is in this reactor. So this is 150 multiplied by 0.667 minus 0.3. And this is equal to 55 moles. So then you can plug that into here, and you end up getting 0.63. So for number 16, because remember I said I was skipping 14 because it's really similar to 10, And for 15, you don't need to know that for the exam. So 16, it says the first order reversible reaction. So you have first order, it's reversible, A to B, is in a flow reactor, so flow. The equilibrium constant at 300 K is 35, so Ke is equal to 35 at 300 K. And the heat of reaction, so delta H, reaction is 5,000 calories per mole. A conversion of 80% is desired, so we want X is equal to 0.8. The engineer designing the reactor contends that you need to operate below 125 C, so T less than 125 degrees C to get that conversion. And so then it wants you to verify if this is correct or incorrect. So what you can do, first of all, he's given you the K at a certain temperature, and we actually want it at a different temperature, so that's what I would calculate first. And you can use the Van't Hoff equation for that. So this is K E T is equal to K E T1 exponent delta heat of reaction over R 1 over T1 minus 1 over T. You can look this equation up. This is derived from this d ln K EQ over D 1 over T is equal to heat of reaction over R. This is the Van't Hoff equation. So anyway, if you go back to this, you can calculate Ke at this temperature. And so you would put in, so this would be Ke T is equal to 35 multiplied by exponent minus 5,000 over 1.987, 1 over, and then T1 was 300 minus 1 over 398. So this is equal to 4.437. But then the problem is asking about conversion and whether you need to operate at, so if this temperature is, like, so if you operate, that you have to operate below 125 in order to get 0.8 conversion. So I'm going to erase some stuff real quick. What we can do is write the rate law. And so for a reversible reaction, minus RA is equal to K CA minus CB over KE. And this is, so this is the, for a reversible reaction, and if you're not sure about how to derive that, definitely make sure you know before the exam. And so the reason why we can use this equation is because for a reversible reaction we can find what's called an equilibrium conversion. And so at equilibrium we know that minus RA is equal to 0 at equilibrium. And so we can set this to 0, and if we do that, we end up with CAE is equal to CBE over KE. And I just added the e's so I know that this is equilibrium conversion. And then we know that CA naught, well, CAE is equal to CA naught 1 minus XE, and CBE is equal to CA naught XE over KE. And so then the CA naught cancels, and I can just solve this for XE is equal to KE over 1 plus KE. And this is equal to 0.816. So at this temperature, the equilibrium conversion is 81%. And we want 80%. And so then to verify this, let's just say that you put a higher temperature in here, like, I don't know, 500 or something. Then you can calculate K. And if you do that, then you'll find that for this as K changes with temperature, this conversion goes, as you increase the temperature, the conversion goes down. So then you can say that that's true, that you do need to operate below 125.